see what we got here. Can we move on? Basically, I was saying, okay, we'll follow up a seminar tomorrow about that will be on how we develop technology, and then these folks will give you some pretty good understanding of how to do the modeling part of oxidation, diffusion, and hopefully ion implantation, which is not the ion implant damage really. It has been modeled, but it doesn't do very good prediction, so it's more empirical. But even though you could model what energy, what range and everything statistically you can implant. You know, in ion implantation, the advantage is obvious because you are not depending on the infinite doping source at the surface and get diffusing to create an appropriate profile. But ion implantation helps you to put a controlled amount of impurities in a certain depth, and then of course it creates other problems like damages and all that, but that can be taken care of. And so therefore the way of integrating impurities in silicon has gone from this surface diffusion, surface impurities and diffusing into the bulk, from that kind of a process, which pretty much ended towards the 1990s. And everything is implanted because we can control it so much better. The amount of impurities and their distributions we can control far better. And as we scale things down, everything is shallower. So we could handle everything much better with more precise range. The only problem with, well, I'll come to that. I'm getting ahead of myself. Let's go. I'm not going to belabor this oxidation kinetics, which has been developed and modeled initially by Grove, and it has been improved by many others over the years. That Partha or Mitashi will cover for you. I'll not cover these because they will cover these. I provided them the information from the Energies lecture series. So they have all the materials, they'll cover that for me. Let's keep going. I think they will summarize the modeling part of it, so I'm not going to spend time on that. Yeah. So this is this hour's lecture. It is on diffusion. The two phenomena we depend heavily on in charge transport of one sort or other, directly or indirectly. That's drift and diffusion. What's the difference? What is drift?
So one is influenced by the electric field and one is influenced, so drift is influenced by the electric field actually.
You said it, absolutely right. Yes. It's charge movement under a field. Very simple. So, it's like going to high, it's like the way the water moves from high to low. So it does either electron or holes, they move in opposite direction with the good of the field. It's very simple. So drift is a very simple phenomenon, but diffusion isn't. Diffusion is a far more complex phenomenon. The original diffusion espoused by Fick's law was focused on either concentration gradient or flux movement within the context of the flux field, that kind of thing. But then that didn't help us very well. So the diffusion the models got considerably improved over the years, which took into account the intimate atomic modeling. So as the impurity species move through the lattice, they get either aided by defects like vacancies, or they basically form either vacancy impurity pair or interstitial impurity pairs. And depending on their nature, they either move or get retarded in movement. So this is a far more complex phenomena than simple fixed laws diffusion phenomena. So that has been extensively iterated, modeled, to a point that quite a bit of good modeling was done on that. But like anything else, the phenomena of nature is fairly complex. So we end up doing a lot of iterating, evaluation, starting from model and finally ending up what the kind of profile we desire. And this is particularly true because we need very precise modeling for impurities as we get, everything goes to the surface, as we shrink everything. So it's particularly true. But it's important to understand some of this phenomenologically, as well as in the actual process environment, how we put the diffusions together, doping the impurities in the desired places in silicon to get the device characteristics. So, diffusion in silicon, intrinsic or appropriately doped, consists of placing dopant source either at the selected surface of silicon substrate or implanting the dopant in ionic form in the selected regions first and subsequently redistributing, which we call drive-in, the dopant within the desired depth, both vertical and lateral, through thermal exposure to heat. Now remember the thermal budget. It's a very important parameter. So we wanted to do diffuse, of course, impurities, right? Without impurities, you cannot play the game, right? But to put the impurities in silicon to the desired way, so that you get the right kind of transport characteristics. Be it linear or non-linear, be it active or passive device. So that is essential. However, we definitely need to understand how the dopant moves in the silicon substrate or lattice, and how it displaces silicon atoms within the context of local lattice structure of the substrate. So basically it depends. Most of the diffusions that we deal with in practical life replaces silicon in the lattice. So they're not what we call interstitial type. There are two types of diffusion. Impurities, one goes preferably to the interstitial side in silicon lattice, and the other one goes to the substitutional side. Substitution means you replace where the silicon atom should have been and end up putting one of the impurities inside. So most of what we deal with today in devices are substitutional type. But theoretically, there are also interstitial type of impurities, and we can talk about it a little bit on that. But they are tend to be somewhat academic. So diffusion from dopant source at the surface, and then I have two parts here. Part is dopant source at the surface, the other one is ion penetration. As you know, that I think since 1990s, since 1990s. We started off with a big doping source on the surface and drive it in. That's the way we used to build the devices. But then when the implanter came, sign implanters, where we could control the amount of dopant far more precisely and put them in certain depth and range far more precisely, we virtually gave away to the old way of doing diffusion. So, for all practical purpose, ion implantation is the means of diffusion since 1990s. And tomorrow I'll tell you how we transitioned VLSI to ULSI. And you'll see we adopted everything ion implantation for all the implants. That was an essential item. We decided a priori, because we cannot deal with the variations in the previous way of putting impurities and drying them in. So we had to go to implantation. So I'll come to that. Okay, quiz. Why we dope polysilicon gate and why we psilocybin gate? Now, why LDD extensions? Okay, let's take one thing at a time. Why we dope polysilicon gate? Now, polysilicon gate, as you know, is phasing out. Polysilicon gate survived starting at 1980 time frame, when we realized the aluminum metal gate, we are running into a variety of problems, including yield and also extendability. Aluminum is a dopant. You don't want a metal to be a dopant. You want the metal to be a metal. So it does not contaminate any form of structure down below. Although aluminum, back in old days, there's another story. There's something called electromigration. Do you understand that? Because in high fields, essentially the metal ions, the atoms start migrating as a function of fields. So you end up having voids and eventually failure of the metal wiring. That phenomenon was found out pretty early in 1980s by IBM experts, who then basically espoused you can't use aluminum metallurgy, even though it's simple and all that kind of thing. So back in old days, it was under trade secret for years. IBM quickly done away with the rest of the world, did pure aluminum wiring metallurgy. They adopted something called aluminum copper metallurgy, which most of these industries did not know the technology and the way of doing it. And that is because of to prevent electromigration and improve the device reliability. So copper has a fair amount of solubility into aluminum, and when they form an alloy, it's far more resistant to electromigration than aluminum itself. So we did away with that metallurgy-wise. But then aluminum copper lasted quite a bit until we needed more stable metal, especially for applications where there's a big range of temperature. A lot of electronics are used in space and for military hardware. So, as a requirement, they wanted to ensure they don't have any kind of field failures with the excursion of temperature, with high power swings and that kind of thing. So we ended up having far more robust metallurgy called tungsten, which is a high temperature metal, very stable. So industry moved from aluminum to aluminum copper to tungsten. I believe for most technology today uses tungsten metallurgy. So that's about the metallurgical part. So either implantation, driving the dopant within the desired depth in the both vertical and lateral profile. Why lateral profile? You need to regulate the lateral profile. Why?
So that least area get and get to cover diffusion को lateral control करते हैं.
Lateral profile. Why is it that important?
Because sir, if much area is under the gate, then more will be the capacitance. I mean, it has to be fixed.
So that the doping is uniform, first get done from both sides, and if we do it from one side, then the concentration on the other side will be more, something like that.
Well, but the source drain is done from the both sides, right? So diffusion is done from the both sides for a field effect transistor. Resistor is trivial, but how about transistor? It's controlling the channel, and you have the source of carrier and the collection of carrier at the two ends. They're done symmetrically. So why is lateral diffusion important?